Welcome to this video on transform settings. This video will be presented in two parts. In the first part, we are going to talk about the nature of transform settings and the varieties of transform faults that we commonly observe on planet Earth. We're also going to talk about the difference between transform and transcurrent settings. In the second part, then we will investigate a number of examples that we can use as case studies in which transform faults and transcurrent faults are important. When we look at the plate configuration of the Earth, we will find that almost exclusively transform faults are developed in the oceanic lithosphere, wherever we have connections between offset segments of mid-oceanic ridges. We will find transform faults, and they can be hundreds of kilometers long, as we see here in the South Pacific. Also in the Atlantic, there are some sizable transform faults with large offsets of mid-oceanic ridge segments. However, there are some locations where transform faults are also cutting through continental crust. The most prominent features are the San Andreas Fault in California and the Alpine Fault in New Zealand, but there are also other ones. Here, the northern boundary of the Caribbean plate that cuts through Guatemala is also a large-scale transform fault separating the North American plate from the Caribbean plate. Here we see the most common configuration of transform faults connecting offset mid-oceanic ridge segments, and if we would assume that the eastern plate that we see here on the right-hand side is growing towards the east, and the western plate here on the left-hand side is growing towards the west, we would have to accommodate the displacement along this transform fault by dextral strike slip, whereas the displacement along this transform fault would be sinistral because the offset direction between the ridge segments is just the other way around. Of course, there are other possibilities. We have here a mid-oceanic ridge that is connected with a transform fault with a subduction zone, with the trench of a subduction zone that forms the boundary to an overriding neighboring lithospheric plate, which might be oceanic or continental. Another variety of transform faults are those transform faults that connect offset segments of subduction zones. Here we see an example where a subduction zone here in the north has a different polarity and a large lateral offset with another segment of the subduction zone further to the south. Here we see the subduction of the western plate underneath the eastern plate, and up here it's just the other way around. The eastern plate is subducted underneath the overriding western plate. These plates here have an irregular boundary, and we see here along the connection between point Y and point X, we need to have a dextral transform fault that accommodates the plate movement of the plate here in the north compared to the plate in the south. In a previous video on continental breakup, we have discussed how transform faults originate, and I just want to remind you to this mechanism. We know that rift grabens can develop according to different kinds of modes. The Wernicke and the Mackenzie are the most commonly known ones, but there are also hybrid models between Wernicke and Mackenzie. And wherever segments of the rift are bordering segments that follow another mode of continental breakup, we require transfer faults that accommodate the different types of strain on either side of the boundary between these segments. We see here in blue the position in which a future mid-oceanic ridge would form once continental breakup is completed. And these transfer faults that accommodate the displacement along these different types of segments then will develop into oceanic transform faults once continental breakup grades into seafloor spreading. There is another video on that. This is a second year level course. Its fourth chapter is dealing with extensional settings, and continental breakup is a part thereof. You might want to check out this other video. The mechanisms of continental rifts that develop according to such different modes is fairly straightforward. We see here the continental stage, a continental rift graben, and because of divergent plate movement, we will see that a dextral strike slip along such a transfer fault is required, and with increasing spreading, we eventually would convert the rift into an oceanic ridge and into a center for seafloor spreading. And the transform fault that we see here succeeds the former transfer fault in the continental stage. From this stage onwards, we will find that new seafloor is created, and we see here indications for different magnetic polarity as you commonly see in seafloor. And we see bilateral spreading and growth of the seafloor according to progressing continental breakup. At some stage, the connection between the two continental plates will be lost as soon as the mid-oceanic ridge segments have produced enough seafloor in order to separate the two continents. There is then an associated feature to the active transform fault that we see here, connecting our two mid-oceanic ridge segments. These are fracture zones, oceanic fracture zones. Here in this example, we are talking about the oceanic situation. So the continental breakup has been completed for quite some time, and we are now in a large oceanic basin. In the continuation, along the strike of transform faults, we will find oceanic fracture zones bilaterally on either side of the offset mid-oceanic ridge segments. And in many textbooks, you will find labels like this: inactive fracture zone. I would say perhaps they are not quite inactive. It's probably more appropriate to talk about less active or inactive fracture zones, because the question whether seismic activity or tectonic displacement takes place along such inactive fracture zones is a matter of spreading rate along these two neighboring ridge segments. If we assume that the northern ridge segment that we see here has a spreading rate of about 3 centimeters per year, and the southern ridge segment has a larger spreading rate, for instance 6 centimeters per year, we will find dextral strike slip, of course, along the transform fault, because the plate A that we see here on the right hand side moves eastwards, plate B moves westwards, but between the part here in the north of plate A, let's name it A1. This A1 is slower than plate A2, and that would cause stress and tectonic displacement along the oceanic fracture zone, and the displacement would be sinistral. We see here, because the northern part of plate A is slower than the southern part, the relative movement along this part of the fracture zone would be sinistral, opposite to the shear sense that we observe along the transform fault. If we look on the western side and evaluate the kinematics along the fracture zone in the west, we will find that there is a dextral displacement, because we see here that the southern part of plate B, let's call it B2, is spreading faster than the northern part of plate B, and that would force a dextral strike slip movement along the western part of the oceanic fracture zone. If the spreading velocities are reversed and the northern part of the mid-oceanic ridge spreads faster than the southern one, the tectonics along the fracture zones would be reversed. In the eastern fracture zone, we would find dextral movement because the northern part of plate A is spreading faster than the southern one. In the west, we would find sinistral strike slip because, again, the northern part of plate B is faster than the southern part of plate B, and that would require accommodation by sinistral strike slip tectonics. Only if we have the same spreading rate in the two ridge segments, the fracture zone would indeed be tectonically inactive. And this would apply to the eastern as well as to the western part of the oceanic fracture zone. The mere existence of oceanic fracture zones implies that at least at some stage in their tectonic history, these ridge segments have been spreading at different rate, because otherwise there would not be a reason to see any oceanic fracture zones. They are indicative of variations in spreading rate in neighboring oceanic ridge segments. If we talk about the transform faults in the narrow sense, that means transform faults that connect two neighboring mid-oceanic ridge segments, there are some characteristics that I want to mention, and the most important one is the length of the transform fault. So the distance from one to the other ridge segment. This length does not change during the evolution of the ocean. The length of the transform fault is defined and is created during continental breakup in the early stages of rifting. That is when we create the offset between neighboring mid-oceanic ridges. That means these are old and inherited structures that go back to transfer faults in the continental breakup stage. And this length does not change irrespective of how active mid-oceanic ridge segments are. The displacement length, however, that is another matter. If we see here the length of the transform fault itself, this can be dramatically exceeded by the amount of displacement. For instance, here we see along the mid-oceanic ridge, quite a bit of ocean floor has already been created, say at time stage number 3. Bilaterally, we have created more seafloor than the length of the offset between the ridge segments. And that means all this oceanic plate material that has been created must have passed along the transform fault and is about passing here the neighboring mid-oceanic ridge. And since we know that oceans can be thousands of kilometers wide, we will find displacement along transform faults that by far exceed the length of the fault itself. If we talk about transform faults in the wider sense, that means not specifically transform faults that connect mid-oceanic ridges, then the situation might be different. If the transform fault connects a ridge with another structure, such as a subduction zone, the fault length may or may not remain constant, and that depends on a number of factors. The fault length remains constant if we are, as we have seen in the previous slide, connecting two mid-oceanic ridge segments. It doesn't really matter how much oceanic lithosphere is created, it will simply pass along the transform fault, and as soon as it is beyond the neighboring mid-oceanic ridge, it will not create very significant tectonic movement along the oceanic fracture zone, which we are not seeing here on this sketch. In this situation here, where a mid-oceanic ridge is connected to a subduction zone, the fault length between the ridge and the subduction zone will remain constant if the subduction and the spreading rates are equally fast. That means that the oceanic ridge push that creates a new oceanic lithosphere is entirely compensated by subduction of the oceanic lithosphere underneath the neighboring lithospheric plate. If that is not so, then we get variation of the length of the transform fault. LF will be decreasing if the spreading is slower than the subduction. So if we have here a spreading rate of 3 or 4 centimeters per year, but here we find subduction that is 8 or 10 centimeters per year, then the neighboring plate will increasingly override and consume the oceanic plate that we see here, and eventually will also override the mid-oceanic ridge, which then gets subducted. On the other hand, if the spreading rate is higher than the subduction rate, then more oceanic lithosphere is created by the ridge, and the trench and the ridge will increasingly separate from each other, and this will make the length of the transform fault grow. Here we see a more complex situation of mid-oceanic ridges and the connecting transform faults that are subducted underneath a overriding plate in the east. We see that here a transform fault develops along a plate boundary, and this transform fault will increase in length the more the neighboring ocean is being subducted underneath that overriding plate. This is a special case that applies to the San Andreas Fault, and we are going to discuss that in more detail in the second part of this video. We are now coming to some features that transform faults and transcurrent faults have in common. Transform faults are the plate boundaries that we have discussed that essentially develop from transfer faults into oceanic structures connecting mid-oceanic ridge segments. Transcurrent faults are any other type of strike-slip faults that we might find also in continental crust. Such strike-slip faults, be they transcurrent or transform, might not always be absolutely straight, and we see here two examples of bending strike-slip faults. Both of them are dextral, and here we see a bend to the right hand side, and here we see a bend to the left hand side. We see that a northern block is moving to the right hand side, and where the strike-slip fault is bending to the right, we will see that the upper and the lower block are moving apart from each other. This creates space at the surface, which leads to subsidence and to the creation of sets of normal faults accommodating this subsidence. This is what we call a releasing bend, or sometimes, as we see here, also called a releasing double bend. A restraining double bend or restraining bend, depending on the textbook that you choose, is formed where a dextral strike-slip fault bends to the left. And here we see that the blocks to the north and to the south of the strike-slip fault move towards each other. We get convergent tectonic movement, and that requires shortening, uplift, and the formation of thrust faults or reverse faults in order to accommodate the block movement towards each other. The structures that form in such situations are shown here in block diagrams. The restraining bend that we see here at the bottom in map view looks like that. We see a dextral movement along a curving fault, and in between we find several segments of reverse and thrust faults, along of which material is moved upwards, and that creates the topographic uplift that is typically seen in young curving strike-slip faults. Such a feature is also referred to as a positive flower structure, sometimes called also palm tree structure, for its obvious geometrical features. Where we form releasing bends along curving strike-slip faults, we will create space at the surface, and several segments, as we see here, will form in combination of the strike-slip movement with a normal slip component, as we see here, and that creates a basin at the surface. This is referred to a negative flower structure, also sometimes called a tulip structure, again for its obvious shape and geometry. Here's a slightly different type of structures that form along strike-slip faults. We have seen that strike-slip faults can bend and curve and therefore produce either releasing or restraining bends. But we also might find step-over structures, and step-over structures form where parallel segments of the strike-slip fault are overlapping but are not directly connected with each other. And again, it depends on the shear sense along these strike-slip faults whether we find contractional structures in the overlapping area or extensional structures. Both have different names. In the case of contraction, we would refer to that area as a pop-up structure, or in the extensional situation, a pull-apart basin. And this is a matter of geometry of the step-over and the shear sense along the strike-slip fault. Here we have a dextral strike-slip fault that is overstepping and overlapping with another segment, and the dextral sense of shear would mean that the northeastern block here moves to the southeast and the southwestern block moves to the northwest. And if that happens, then in this area here where the two strike-slip faults overlap, we will find contractional features. These contractional structures will be reverse or thrust faults which contract the crust in this area simply because the two blocks are running into each other in that area. And again, if we are talking about recent tectonics that are still active, it is very likely that we find in this area a topographic high because material is pushed together in this area. If the offset is just mirrored to this case, we will find that the displacement along the two fault segments that we see here creates space in the overlapping area. Again, the northeastern block is moving to the southeast, the southwestern block is moving to the northwest, and that creates space in the overlap. And together with that, we can expect to find normal faults or oblique slip normal faults with some strike slip component, and the creation of a basin at the surface. This might then be a sink for sediments to be deposited synkinematically. We also can see that pop-up structures and pull-apart basins can occur at the same time in the same strike-slip fault zone because the step over might be in opposite directions along the strike of such a longer, larger scale strike-slip fault. So important in pop-up structures, the geometry of the strike-slip shear sense and the step over requires contraction and the formation of contractional faults, whereas in pull-apart basins we find the opposite. Obviously, according to the name, we are pulling apart the two blocks, create normal faults and depressions into which a young sediment can be deposited. There are further terms that describe this situation. You might find in the literature the terms restraining and releasing step overs. It's exactly the same. We see here in plan view what we see here. A configuration of overstepping dextral fault segments, which create here a restraining step over and a pop-up structure, and a releasing step over that creates a pull-apart basin. Other than transform faults that have a specific beginning and a specific end, normally two neighboring mid-oceanic ridge segments or a mid-oceanic ridge segment and another type of plate boundary or a subduction zone, transcurrent faults that we observe in the continental crust often have a kind of a diffuse ending, and very often they form splays. Splays are secondary faults that form at the end, at the lateral end of strike-slip faults, and they often form complex structures that we see here, either sets of curving normal faults or curving thrust faults, depending on the direction of displacement and the direction in which these secondary faults are curving. So these splays, also sometimes called horsetail structures, they might form in either direction, left-handed or right-handed. In this example, which is probably the more common situation, is a curving and a splaying of a strike-slip fault that dies out in the direction of sigma 1. And if that takes place and we curve from a main strike-slip fault into the direction of sigma 1, then we will create oblique slip normal faults. We see that here in the block diagram, a tapering out, a fizzling out of a transcurrent fault into such curving segments due to the movement of the neighboring blocks. This will create space and will create oblique slip normal fault segments, very often with Lystric fault geometry that we see here. Reverse or thrust faults will occur if the splays are curving into the direction of sigma 3. Here we will find that the dextral movement in our example here will create contraction, and accordingly we will form sets of oblique thrust and reverse faults, perhaps associated with folding if this happens in a crustal environment that allows semiductile deformation. And these splays would then form geometries that we see here in the block diagram, again with Lystric reverse, oblique reverse and thrust faults separating different blocks from each other that accommodate the contraction that is required in such places. Here we see a summary of all associated structures with strike-slip faults, particularly applicable to transcurrent faults in the continental realm, with dextral fault examples and the contractional and releasing bends, or the step-overs with pop-up structures or pull-apart basins. The same is shown here for sinistral strike-slip faults, where we find pull-apart basins, pop-up structures, releasing and restraining bends, depending on the geometry of the step-over and the shear sense of the shear zone. So summarizing transform faults and transcurrent faults, if we are looking at transform faults, even in the wider sense, they are always plate boundaries. There is an active portion that will end at a fixed point where it will intersect with other structures, the mid-oceanic ridge most commonly, but also possibly a subduction zone or other forms of plate boundaries. The fault length stays constant if the transform fault connects mid-oceanic ridge segments, but it may change if a transform fault connects to a subduction zone or any other plate boundary. The displacement along such transform faults is typically very large because it needs to accommodate the seafloor spreading, which might be thousands of kilometers of oceanic lithosphere. If there are curving segments, the kinematic character of the strike-slip fault might be either transtensive with an extensional component of strain, or transpressive if we have a contractional component of strain. Transcurrent faults are those kinds of normal strike-slip faults that we observe in continental lithosphere. They typically die out in some form, and very often that might be splays, which are arrays of faults, as we have seen, horsetail structures. That is also a commonly used term for them. Or they might even, depending on crustal depth where they develop, disappear into a diffuse zone of plastic strain, particularly if they form in the lower green schist facies in the brittle ductile transition of the continental crust. They are not normally plate boundaries. Transcurrent faults are typically intraplate features. The displacement correlates with the fall length. If you just try to displace two blocks within a plate along each other, you have to grow the fault length the larger the displacement is to be. Large-scale strike-slip faults in the continental crust also imply that there was large displacement along these structures. Curving segments, step-overs, and splays are kinematically identical to such situations in transform faults, but curving segments, splays, and step-overs are more common in transcurrent faults than they are in transform faults. This was it for part 1 of this video. In the second part, we are looking at a few examples of transform faults and transcurrent faults in the oceanic and in the continental lithosphere. Thank you very much.